We're going to find the area under a curve today using geometry. So for the first one, how do we find the area under this curve? Well, we can split it up into different geometric shapes. Okay. So the area of the underneath the red line would be 1/2 base times height. The change in x would be 1, and the height is 2. So I get 1/2 times 1 times 2 is 1. So the area of this section is 1. Okay. The area of the blue section is 2 times 2. The change in x is 2. So the area is 4. The area of a trapezoid is base 1 plus base 2. So I have 2 plus 1 divided by 2, and then times the change in x. So times 1. So I get 3 over 2. Yeah, 3 over 2. Okay. Or 1.5. And then the last section is a square. So 1 times 1 gives me 1. We just add those up. Love myself an area model. So 1 plus 4 plus 1 plus 1.5 gives me 7. So the area is equal to, or 7.5. 7.5 units. Okay, so that's what we're going to do today. We're going to make an approximation of an area underneath a curve using geometry. So yeah, what happens if our graph is curved? What we do is we create rectangles. And we either create a rectangle where we use a consistent rule. So we either create rectangles where the left endpoint is the height of the rectangle, and then we build rectangles out like that. Okay. Or we use the right endpoint of our rectangle to build a rectangle, or mini rectangles. Okay. And then we add them up. So it is an approximation where you can see this right Riemann sum is an overestimation, and sometimes, like this one, is an underestimation. So we know that, talking about overestimations and underestimations, we know that if the curve is positive, so it's increasing, the curve is increasing, and we're taking the left Riemann sum, that it is going to be an underestimate. If the curve is increasing and we're taking the right Riemann sum, it's an overestimate. If the curve is decreasing and we're taking the left, so this is decreasing and left Riemann sum, it's an overestimate. And if it's decreasing and a right sum, it's an underestimate. Okay. So how do we get a better estimate? Let's see. We can take a sum where the change in x sections are not equal. Okay, that's one option. We can also take a sum where all the change in x sections are equal, so equal intervals. But the way we get a better estimate is that we use narrower and more rectangles, smaller and smaller, and so narrower and narrower and narrower rectangles. So something like this, you see where the change in x is smaller and smaller. Okay, so this is the change in x is a smaller value. Okay. So how do we find the area of each rectangle? It's well, for evenly distributed rectangles, so like if I were to split up this section here so I have an interval from 0 to 2, and I want to split it up into 4 intervals, even intervals. What I would do is use this formula. My endpoint subtracted divided by the number of intervals I want. So this is going to be the number of intervals. So I do delta x will equal 2 minus 0 over 4, giving me subintervals of 1/2, or change in x of 1/2. I have to write very small. Okay. But it's okay to have uneven distribution of intervals, but each change in x will be different then. So looking at this example, each change in x is a different length. And that's okay. It's just not as easy to calculate. Okay. All right. So what we're going to do is add up all the rectangles, basically. Okay. And we use this notation, which we'll see again later in the class. So this is summation notation. So it says we're taking the sum of this formula, basically. Okay. So we have, you know what? I forgot something here. I forgot to tell you that each one of these rectangles here, if I take a right Riemann sum, is the height, which is equal to f of x at your point, okay, times the change in x. So the area of a rectangle is equal to delta x times the change in x, f of x, okay? So we have, I said that wrong. That is delta x times f of x. So delta x times the height. Our summation notation, what this means is the sigma means the sum of, okay, and I equals 1 is your first term. At the top, n is the last term. So it's a placeholder. It's going to keep going till n. So that n could be a 5, a 6, a 7. It could just be a variable saying it's going to go on until some unknown number. Okay. The right here is the formula for the terms. Okay. So it says we need to use f of x sub I times change in x. So remember, I is the number that is going to change. We're going to start with x sub 1. So everything stays the same except for we're using x sub 1 instead of x sub I. Then we're going to add the next term, f of x sub 2, okay, times delta x, plus f of x sub 3, dot, 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 forever until we get to f of x sub n minus 1 plus f of x, our last term, f of x sub n. So we're just adding each one of the terms together, okay? After I see that I can simplify this function a little bit, each one of the terms has a delta x in it. So I'm going to GCF the delta x out, and then I'm just multiplying by the height, the first height plus the second height plus the third height plus the fourth height, so on and so forth. Okay, so fun fact, actually a really important fun fact, is that we can get the exact area under the curve by taking the limit as n goes to infinity. So as we make infinity rectangles underneath the curve. Okay, so we'll come back to that later. We're going to practice with some sigma notation right now. So the formula is I. We're starting with 1 and we're ending at 6. So when I expand this, this is going to look like, okay, so instead of I, I'm going to put a 1, then a 2, then a 3. So I is being replaced with each one of the numbers up to the last term. That's it. Okay, let's do the next one. So the sum of I plus 1, so instead of I plus 1, we're going to start with 0 this time. So 0 plus 1 plus 1 plus 1 plus 2 plus 1 plus 3 plus 1 plus 4 plus 1. And our last term, we're going to substitute 5. Okay. All right. Last one, starting with I is equal to 1 and ending at n. Okay. So I'm only replacing where, oh, I wrote this down wrong. This should be I, oh, I'm going to replace this with, what am I replacing? Okay, this guy right here, instead of I, it should be K is equal to 1. K is equal to 1. So we're only replacing a variable in for K. So I get 1 over n times 1 squared plus 1 plus 1 over n times 2 squared plus 1 plus 1 over n times 3 squared plus 1. And I'm tired of writing, so I'm going to put plus dot dot dot. This pattern continues to 1 over n times k, or times n, sorry, squared plus 1. That's our last term. So that's how we expand sigma notation. All right, so the next thing we're going to do is we're going to use our Riemann sum to estimate the area underneath this curve. Okay, so first we're going to take the left Riemann sum and then the right. So I'm going to do the left over here, and then we're going to do the right. All right, so I want to split up my interval into four equal intervals. So to get my delta x, I'm going to take my a and my b and subtract them. So 1 minus 0 over 4, it gives me a quarter. So I know I have to split up the domain into 1/2, 1/4, 1/2, 3/4, and 1. Okay, and then I'm going to go ahead and sketch in little lines here so that I can make my rectangles. Okay, so a left endpoint means that I would make a rectangle starting at f of 0. Okay, and then I go over and down and connect at 1/4. That's my first rectangle. My second rectangle is at the height of f of 1/4, and then I sketch it down. Okay, my third endpoint would be at f of 1/2, and then I would sketch it down. And then the last one, I kind of feel like Bob Ross right now. We're going to make our height at f of 3/4, 3/2, no, 3/4, and then sketch it down, 3/4. Okay, so now it's just like pure calculation. So I like to build a table. I'm going to do x and f of x. So at 0, 1/4, 1/2, 3/4, and I'll just put in a 1 because we need it later. I typed this into my calculator and I got 231 over 16, 7 over 4, 23 over 16, and 1. Okay, so to figure out our area, we say that the area is about equal to, it's an approximation, the height. So remember, each rectangle is delta x times f of x. Okay, so I'm going to take my delta x and multiply it by f of my left side of the purple triangle would be x sub 0. Okay, plus delta x times f sub x sub 1 plus, you know what, let's do it like this instead. F of 0 plus delta x times f of 1/4 plus delta x times f of 1/2 plus delta x of f of 3/4. And then I don't have to worry about f of 1 since that's on the right side of the rectangle. All right, so we're just going to substitute in. I'm going to GCF my delta x to the front. So I get my change in x is 1/4. So 1/4 times, okay, f of 1/2, f of 0 is 2, plus f of 1/4 is 31/16, plus f of 1/2 is 7/4, plus 23/16 for f of 3/4. And I get area is about equal to 1.78125. That's what it's about equal to on the left-hand side. And remember, this is an overestimation. The curve is decreasing, and we're taking the left-hand Riemann sum. All right, let's do the right-hand Riemann sum. So I have area is about equal to, and I'm going to split this up nicer than that. Something weird happened with my computer, so I'm just going to walk you through this right Riemann sum again. So, wow. All right, we have, when we take the right Riemann sum, we want to use the right hand height of the rectangle. So we're going to take the Riemann sum with the height at f of 1/4, f of 1/2, f of 3/4, and f of 1. Okay, so we have delta x, since all of the change in x's are the same width, they're 1/4, I can just GCF it out to the front. And then I get the height at f of 1/4, the height at f of 1/2, the height at f of 3/4, and the height at f of 1 right here. And we get, using my table from the left-hand side, f of 1/4 is 31/16. F of 1/2 is 7/4. F of 3/4 is 23/16, and f of 1 is 1. Combine those to give me an area of about 1.53125. And it's an underestimate because the curve is decreasing and we are taking the right Riemann sum. The rectangles are going to be smaller than the curve. All right. Okay, so next we have we're going to find the left and the right Riemann sum using this table. And right away, what I noticed is that delta x, that we do not have equal intervals. Oh, I should put unequal intervals. Okay, and that's okay. We just can't GCF out the delta x into the front. So I'm going to make an interval right here. So that's where I'm making my column. Another rectangle here, another rectangle here, and another rectangle here. I'll make it like this. Okay, so I see that delta x is equal to 2, delta x is equal to 3, delta x is equal to 2, and delta x is equal to 1. And that is A-okay. So for the left, I'm going to do it right underneath. The left, I get the area is about equal to delta x times f of x. Okay, so the left is going to be at f of 0. So I have 2 times f of 0, which is 0, plus, okay, next is delta x is 3 times f of 2, which is 4, plus 2, that's my delta x, times f of 5, which is 13, plus 1 times f of 7, which is 21. When I add that up, I get area is about equal to 59. Okay, let's do the right. Same intervals, but instead of using the left hand endpoint, we're going to use the right. Okay, so area is about equal to 2 for my delta x times 4 plus 3 times 13 plus 2 times 21 plus 1 times 23. So I get area is about equal to 112. And in this case, you can see that the right-hand curve is an overestimate because the values are increasing. So the right-hand curve is going to be an over and the left is under. Okay. And that is it for right and left. We're going to look at mid and trapezoid next.